Hello, this is the fourth video on Fourier series, and here we're going to look at the Fourier series in a little different way. We're going to create an orthogonal basis for it and use that approach, and that'll make more sense. Let's in a minute. So let's just jump right in. So a little background, very briefly, on vector spaces. So let's say there is a space called S, and we have some basis vectors for our space. And so these span this space. So, and then of course with any vector space you need an inner product. And here we're going to use the standard inner product, often called the dot product, which is just this, xj dotted with xi is just this linear combination. So now we're going to call the basis orthogonal if the product or the dot product of any two of these are zero when they're not the same, and of course non-zero when you dot it with yourself. So now this is the key point for the Fourier series I want to make analogous in this vector space. So if we let V be a vector in this space, it can be represented as a linear combination of these basis vectors. Now that makes perfect sense, and so when we go into the Fourier series I'm going to point back to this, and since this makes perfect sense, it should make perfect sense for the Fourier series. So how do we solve for the AIs? We use orthogonality. Okay, what does that mean? Well, if we have V represented like this, and each of the linear combination, each of these vectors are orthogonal, so that means when you dot them with any other vector, they're zero. So let's just pick an arbitrary one, call it, the ith vector, the ith basis vector. So when we dot it with this vector, and then that goes into each one of those, since they're not, if it's not the same vector, it's zero. So the only one that's non-zero is the ith vector. So ith vector dotted with itself is non-zero. So now this is a number, as you can see right here. So if we divide that to the other side, we get the ith coefficient, and then so we can repeat this with each vector in the basis, and then we can solve for each AI. Okay, and it should be noted that the solutions for these AIs are with respect to this inner product, because we developed this inner product to be which made these basis vectors orthogonal. Okay, so now let's move on to Fourier series. So we're going to create, a vector space, vector in quotes, of functions. So instead of vectors, we're going to create a basis of functions such that we can express that any function in our space with the linear combination of our basis functions. Okay, so this here represents, it's this. So we take our basis functions, here basis vectors, linear combination, we can create any vector. So here we're going to create any function of a span of our basis functions. So now these basis functions have a common domain, and then it creates functions that are valid, in that domain. So what is so interesting? So what basis functions can we use? And they have to be orthogonal. So any two functions multiplied by each other by whatever inner product we choose is zero. So there are several bases that we can choose, and which some of them or have heard of. Bessel functions, Legendre polynomials, and Hermite polynomials. Those can be basis functions that when we take a linear combination of them, will create other functions. Okay, but for the Fourier series, we're going to choose sine and cosine functions as our basis functions with respect to this inner product. And we're going to say f dotted with g, and you can either write it as this or as a tuple, and it's going to be this integral from negative pi to pi. And so we want any two functions in our basis using this inner product to be zero. So we want an orthogonal basis. Now, using F3, that means the third video in the Fourier series, we can show that these basis functions are orthogonal. The product of any two of these is zero with respect to this inner product. So a quick example, so if we take 1 dotted with sine of x, and that can be any one of the signs, that's represented as this integral, which can easily be shown as 0. So these two functions, the constant 1 and sine of nx, they're orthogonal with respect to this inner product. In the same way, if we take 1 dotted with any of the cosine functions, it can be easily shown to be 0. So this, and then the dot product of any two of these functions is what the magic of F3 was, what we showed there. Now, there's only one little caveat, which we're not going to cover, but I feel that to be complete, I need to mention. Okay, so this inner product needs just slightly more structure than what we're going to give it, because it violates this property of inner products, and where if you dot a vector or a function with itself, it must be positive, and this inner product can violate this property. You can have a function dotted with itself but be 0. Okay, so but in actuality, this is a very, very minor detail, and it's easily fixable. You can create what's called equivalence classes for functions, and anyway, we're not going to cover that, but it's just an FYI for further research when you delve more deeply into this topic. So let's look at a Fourier series. So f must be integrable in this domain and periodic with period 2 pi. And that's what our basis functions are. They're periodic with 2 pi. Now, they're all periodic with period 2 pi. Some of them have a period less than 2 pi, but all periodic within 2 pi. So now this is it. And this is so magical. So any function that fits this, it's integrable, periodic with 2 pi, can be represented like this. And notice that 1 is a basis function. All these cosine values are basis functions, and all these sines are basis functions. So this is literally a linear combination of our basis functions. Right? So here's our basis function. So we take a linear combination and boom. Now, how do we solve for the coefficients of these constants? Well, just like we did in a vector space, where when we dotted this function with with each individual basis functions to create orthogonalities. And that's how we're going to do it. So now, first, let's multiply by 1. And now 1, of course, was that first function in our basis. So when we multiply everything by 1, nothing really changes because you're multiplying by 1. But all of these functions are 0. All of these functions are 0. The integral of this is 0. And the only one that's not 0 is this one. So, and these are non-zero. I mean, these are 0 because they're orthogonal to the 1 function. Now this is, the integral of this is 2 pi, so the 2's cancel and we get a0 is pi. So now to solve for a0, we just divide by pi to both sides. And this is our constant, a0. Now we keep going. So now let's multiply by another basis function. So let's pick one of the cosine functions. And this I is an index, meaning, you know, it could be 1, 2, 3, 4. And just before I was doing this video, I was like, oh, I really shouldn't use I, because I can be represented as the complex or an imaginary number. And Fourier series, probably towards the end of this series, we're going to potentially talk about the Fourier series in the complex world. And so I really shouldn't have used I. But in here, this means it's an integer. It's just an index from 1 to infinity. And so this represents one of the basis functions. So we take this and multiply it times each of the, the left side and the right side. So now this is, well, whatever it is, and this multiplied by 1 is 0. We just showed that on page 1 or 2, page 2. And then all of these are orthogonal except for the ith component, which is non-zero. The rest are 0, and that is due to f3. And the same thing here. These are all orthogonal with respect to our inner product. So you can go back to f3 and note that the only one that's non-zero is the ith term in here, and it's equal to pi. So now we can solve for every coefficient ai. Just divide both sides by pi and you got it, and that's it. And we're doing this by orthogonality. Now there's only one thing to do, is now we multiply everything by one of the sine functions. And so again, this is I is 1 to infinity, and this represents a particular sine function, in our basis. And we integrate, so we multiply everything by sine. This is what it is. This is orthogonal, so it's 0. Every one of these is orthogonal to each other, so it's 0. And the only one that's not 0 is the ith component of this sum. And again, by f3, this is bi pi. So we can solve for bi, and it's this. And so now we have a solution for every coefficient in our for our function. So now let's do an example. So in this example, we're going to let our function be pi squared minus x squared. And we're going to let this function have domain negative pi to pi, and we're going to assume it's periodic in the rest. So basically what it does is it's going to repeat every 2 pi. Now we need to start solving for the coefficients. So we take, remember, a1 was, it's the integral here. Oop. So we have to find this integral, or a0, I meant. So we integrate f of x over this integral, and we get 4/3 pi squared. In the same way, now we solve for the other a-n's, and so we take cosine in x times f of x and integrate, and this is going to be our coefficient in, and for that n here. So now I have to do it. I multiply it, create 2 integrals. Well, this one is 0 because it's orthogonal with respect to 1. This one we need to do integration by parts. So if we let it be this, then this breaks down into this here. Well, this is, plug in pi and minus pi, you get 0. So this piece drops out, and then that minus, when we multiply it in, makes that a plus. So then we have to do integration by parts with this, and we get that, and then we're here. And now this integral is actually orthogonal to 1, so this is going to be 0. and we look at this. So now we evaluate this at pi and negative pi, and we get this, and then the pi cancels, or the pi cancels, and we get this. And then n, for different values of n, so 1, 2, 3, it's either 1 or negative 1. And based upon n, we get this value. It's minus 1 raised to the n plus 1 times 4 over n squared. Now we have to solve for the bn's. But by video 5, which is actually the next video, and the fact that f is an even function, all the bn's are going to be 0. Then now we're finished. We know these functions, we know these constants. We just solve for the an's, and we know a0 is this. So this is the the Fourier series for our function, and we're done. So when this goes to infinity, this equals this, and it's kind of neat if you print this out for expanding terms. This function it's basically this. It's an upside down parabola. And when you do these, they just wiggle about this, and then of course this function repeats, so it goes wiggle, it's wiggle, 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 like this. And then as the terms get bigger and bigger and bigger, those wiggles get smaller and get very, very close to this function. But now let's plug in a value for our function and our Fourier series. So let's plug in x equal pi. So we get pi squared here, and we get either 1 or negative 1 here. So that's 0. That's constant. And then if you do this, when n is 1, this becomes a negative value. When n is 2, it actually becomes a negative. So we just factor it out and we get this. Now if we take this and add it to this side and then divide by 4 to get rid of that, we get this. And what's interesting about this, that's the famous Basel problem that Euler was made famous for by solving. So, well, anyway, that's all I have for today. Hopefully you enjoyed it. If you did, please like the video and subscribe so you don't miss the next one. Thanks. Bye.